"25 years ago, Stephen Hawking invited me to his office to discuss the Big Bang. That was his idea of a job interview. This is how I found him at the theoretical physics department in Cambridge, in England, surrounded by everything that a theoretical physicist at the time needs. Lots of books, a blackboard, and a picture of Marilyn Monroe on the wall. Stephen had already lost his voice by then, but he could talk through a speech synthesizer which was mounted on his wheelchair, which he directed with a little mouse, which was carefully placed in his hand every morning. And this is what he asked me during our first encounter.
The universe appears designed. Why is it the way it is?
So, good luck with your next job interview. What does he mean? Of course, we're familiar with this appearance of design from the biological world. But when a physicist or a cosmologist talks about the notion that the universe appears designed, he doesn't quite mean life as such. He means that the universe, when we look out into space, appears strangely biophilic. It appears that the conditions for life to be possible are ingrained in the basic workings of the universe. So if you look at these cosmic clouds, these are images of the James Webb Telescope, you see the organic molecules, you see the building blocks of life already out there. But of course, the universe wasn't born with these clouds. These clouds, the universe, the Milky Way, is the result of 13 billion years of cosmological evolution. That cosmological evolution is governed by the laws of physics. It's at that level, at the level of the laws of physics, that you see the most mind-boggling level of design. It turns out that the laws of physics have a whole list of properties that if you change any of these, the habitability of our universe, the fact that we überhaupt form stars and galaxies and atoms and molecules and life, the habitability of the universe falls apart when you change the laws of physics ever so slightly, when you change the way the particles interact, when you change the composition of the universe, or if you wish, when you add one or another dimension of space. So it appears, and that's what Fred Hoyle famously said, it appears that the universe is a fix. And it's crazy. It appears that the universe, at the level of the laws of physics, has somehow known all along that one day it would be our home. And it is that crazy question which was apparently on Stephen's mind when he happened to interview me. So in order to tell you the story of my collaboration with Hawking, we didn't immediately find an answer to this question. I have to take you down to a journey, not just in space, not just a journey about physics. I have to take you on a journey to the very roots of physics. Where do the laws of nature come from? What is the basic, what do they mean? Yeah, where do the laws of nature come from? How did we think of laws of nature? In fact, the idea that there are things like the laws of nature goes back millennia. It goes back to the ancient Greeks. Anaximander wrote for the first time that there might be, by analogy with laws governing society, who knows? Maybe there are also laws governing the natural world. But of course, the ancient Greeks didn't identify what these laws are, how we should think about physics, how we should write them down. It took ages and ages, really till the scientific revolution, when people identified the deeper nature of the laws of physics, right? It's with Galileo and Newton. Since the scientific revolution, we think of the laws of physics as mathematical relationships, as some sort of barcode behind the universe, transcending the universe, some sort of Platonic mathematical truths. And in fact, Newton, already in his Principia, sort of promoted that idea. Newton was not unlike Anaximander, who thought by analogy with society. Newton thought about the laws of nature by analogy with godlike laws. So he thought about the laws of nature as absolute truth. That idea became substantiated in the 19th century when, for instance, the law of gravity of Newton was extremely successful. So there is this famous story about a French astronomer, Le Verrier, who was calculating with Newton's laws and concluded that if Newton's laws were correct, there had to be another planet even further than Uranus. Otherwise, the orbit of Uranus was just not correct. So he calls up his friend astronomer in Berlin with a telescope and said, look there on the sky. There must be another planet. So the guy looks, and indeed, he finds Neptune. So that kind of thing, so whatever you guys think of the French, they found a planet just by calculating, and this was a big thing in the 19th century, right? So this idea of the mathematical laws as sort of governing, transcending the universe became very popular. That's also how Albert Einstein thought about it. Albert Einstein famously came up with the idea of an ultimate law of nature. It's sort of the natural consequence, right? If the laws of nature are mathematical truths, there should be some sort of final, unified, ultimate theory governing the universe. So the answer that people like Newton and Einstein would have given to Hawking on what should we make of the design of the universe, the answer that Newton and Einstein would give is its mathematical necessity. The universe has to be like this. But you see, Einstein is looking a little puzzled. And indeed, strangely enough, it's Einstein's own work that began to undermine this idea of an ultimate transcending final theory. And so I have to explain you that in order to get to the crux of my work with Hawking. And I'm going to explain that to you by taking you back to your glory days where you were enjoying mathematics. And here is Einstein's most famous, most deep equation. And it's not E is mc squared, right? And I'm gonna, this looks like Chinese, but trust me, it's very easy to read this equation. We're gonna read it together. The equation has a left-hand side and a right-hand side. On the left-hand side, there's a mathematical expression for the shape of space, the geometry of the universe. On the right-hand side, there's a mathematical expression for the stuff inside space, matter, particles, stars, anything. And of course, as it goes in physics, the magic is the equal sign in the middle. The equal sign in the middle, it's the coolest equal sign you're gonna ever see. It relates the shape of space, the invisible fabric of space around us, to the stuff inside space. This is how it works. You take the Earth, the mass of the Earth will, according to this formula, slightly bend the invisible fabric of space around us. It will create some sort of valley. What will that do? It will keep an object like the moon nicely in orbit around our planet. It's that geometry, that shape of space, That's what we experience as gravity. So Einstein essentially identified the source of what we call gravity. The source of what we call gravity is the shape of space. Put differently, Einstein took space and time from being metaphysical entities that are just there. He took them into physics. He turned them into a physical field, as we say, just like the electromagnetic field, a field that interacts with matter and gives rise to gravity. And of course, you can exaggerate. You can put a lot of matter inside a small region, and you know what's going to happen. If you put a lot of matter inside a small region, the shape of space is going to deform further. It's going to develop a throat-like structure. So that if you have a lot of matter, the bending deepens. And now you can imagine a light ray shooting in there. If the curvature is so deep, the light ray will get trapped. It will get trapped. That's a black hole. A black hole, you've all seen one, is nothing. The black disk in the middle is nothing but a sort of throat in the fabric of space that even traps light. So light cannot escape from a black hole. And it gets really fun when you take two black holes which orbit one another. The fabric of space will have to react and will create ripples. These are these famous gravitational ripples propagating at the speed of light, going through everything, going through stars, through galaxies, through everything. And when they pass the Earth, what will these ripples of space do? They will make our planet wobble and shake. This is exaggerated, of course, but you get the idea. In fact, in reality, these wobbles of these gravitational waves, these wobbles of space-time, are extremely tiny. The biggest explosions of such wobbles, they change the diameter of the Earth by just the diameter of a single atom. So you need exquisite observatories. These are telescopes. Observatories not sensitive to light, but sensitive to gravitational waves, ripples of the invisible fabric of space, which Einstein turned into a physical field. In a way, Einstein made space and time come alive. So that's all fine. So what's the problem? As it happens, the problem came from Belgium. This is Georges Lemaître, who was a priest astronomer in those days working in Leuven. And what did Lemaître do? Lemaître looked at the Einstein equation and he realized that for the very first time we had an equation, a scientific theory that should enable us to tell us something about the universe in its totality, about all of space. And so what Lemaître did, he took all the matter in the universe, all the Milky Ways, all the stars, and he put that on the right-hand side of the equation. And he walked over to the left-hand side, to the shape of space side, 1927. And he notices, to his surprise, that space in its totality cannot just stand still. This equation of Einstein implied that the universe had to expand, that space had to be stretching. And then he did the most amazing thing ever. He said, wait a minute, I can turn things around and go back in time. And he arrives at a moment in the past where the fabric of space destroyed itself. That was the discovery of the Big Bang. The beginning of time, the origin of time, not just an explosion, but the most profound origin you can think of, the origin of the basic fabric of space. Now, what do you do when you discover the Big Bang? Well, Lemaître, I told you, Lemaître was a priest, so he couldn't tell his wife. He couldn't quite tell the Pope either. But of course, he had to tell Einstein, and he did. He told Einstein about his discovery here in Brussels. The two met up in October 1927 outside the Solvay library. And you can see that this conversation did not go very well. Right? Einstein was not pleased with Lemaître's playing with his theory. And the reason that Einstein was not pleased was very simple. When Lemaître took the universe and used Einstein's equation to run time backwards, an expanding universe shrinks and destroys itself. But at the moment of the Big Bang, it's very clear from Einstein's equation. Also, Einstein's equation goes down the drain. Strictly speaking, reading Lemaître's discovery of the Big Bang, you have to conclude that the actual beginning, the Big Bang, the origin, is not part of science. And so, of course, Einstein was not pleased, because Einstein was looking for the ultimate theory that had to explain, in his view, how the universe should be, the biophilic character, everything. And so it seemed from Lemaître's discovery that this was just impossible. Interestingly, and then of course it didn't help that Lemaître was a priest and so forth. You can imagine that story, right? But interestingly, for historical correctness, it was not the idea of Lemaître to put God in the beginning, not at all. In fact, Lemaître made these sketches in his little pocket notebook. He made his sketches of. It's funny, his notebooks. You have these poems, you have shopping lists, you have spiritual stuff, you have things he wanted to say in the Mass, but you also have these cosmic diagrams depicting the evolution of the universe. And here, all the way in the beginning, he writes atom. He called the Big Bang the primeval atom. And he used that term to indicate that, yes, Einstein's equation goes down the drain, but maybe there's a deeper theory, a quantum theory, that somehow allows us to bring the actual origin within science. But he did not, and this is crucial, he did not mean to imply that the beginning would contain this entire biophilic, miraculously fine-tuned universe that we have today. In fact, he said at some point that in absolute simplicity, at that primeval atom, no physical questions can be raised. A typical sort of poetic way of expressing some intuition, which at the time was way beyond any scientific theory, any equation you could ever write down. Indeed, Lemaître never wrote down a single equation what that primeval atom could or should be. But his general idea that the universe emerged from a hot Big Bang was proven correct decades and decades later with the discovery of what we call the cosmic microwave background radiation. It's the afterglow of the Big Bang, filling the universe today, filling this room, filling everything, being everywhere. We are immersed, we have learned, in the afterglow of the Big Bang. And this is a sky map, a projection of the sky around us, indicating not the stars, not the galaxies, but simply the temperature of that primeval radiation. And you see the Big Bang, the early universe, was flickering. The temperature was not the same everywhere. There are slight temperature variations. The difference between red and blue is about 10 to the minus 5 degrees. Very, very, very small. But look what happens. Look what happens when you evolve this young universe forward in time, once again using Einstein's equation. You see that the regions where the temperature was just slightly warmer in the early universe, that those regions is where the stars eventually, millions of later, were born. Slowly you develop larger structure, galaxies, even clusters of galaxies, new generations of stars, and one star, our sun, with a planet that turns out to be habitable and then ultimately the satellite with which we map out that history. So there you have it, 13 billion years of evolution squeezed into a minute, and none of this would have happened if the Big Bang hadn't been slightly flickering, if there had not been slight temperature variations, 10 to the -5, none of this would have happened. Those flickerings of the Big Bang are probably the most mind-boggling biophilic features of the universe. It connects the earliest stages of the universe to where we are now. But as I said, neither Lemaître, nor Einstein, nor anyone else could get a grip on the Big Bang itself, could explain why it was flickering, could explain why this particular soup of particles encoding the conditions for life appeared out of this giant explosion. And so I sometimes say that the Big Bang is the cornerstone and the Achilles heel of modern cosmology. It's the cornerstone because this idea of an expanding universe fits all our observations, and yet if you don't get it, if you don't start it in the right way, your entire edifice of cosmology just falls apart. And that's the historical background behind my conversation with Stephen Hawking. And this was 98, and Stephen was already famous, and he had already written his book, Het Heelal in Dutch, A Brief History of Time. And the highlight of his book of 1985 was that in that book, Hawking essentially proved Lemaître right. In that book, you find the very first and only equation describing what Lemaître called a primeval atom. In that book, Hawking showed that it is possible to get a grip in a scientific manner on the beginning of the universe. And he uses this indeed, as Lemaître predicted, by going beyond Einstein's theory and thinking about the origin quantum mechanically. The problem was that out of Hawking's primeval atom in this book came an empty universe. Not at all the universe we live in. And so by the time I met him, in a way he was back at square one. On the one hand, he had this very strong intuition that the Big Bang was knowable. On the other hand, the model he had invented, he had discovered, was getting nowhere. And so the situation was this. This is the question, what should we make of this design? Is it a scientific question? Is it mathematical necessity, as Hawking and Einstein would like to believe? Or is it something completely else? In the 90s, the idea of a multiverse became very popular. Maybe there are many universes. Maybe the fact that it appears designed for us is just an accident. Or maybe it's none of the above. Maybe something else was going on. So we turned around this problem for quite a few years. And you're beginning to feel, I think, that this is not the usual homework problem. Until I think we had an eureka moment in 2006, and I will let Stephen explain you this. There we go.
I have changed my mind. A brief history of time is written from the wrong perspective. We are not angels who view the universe from the outside.
So as you can feel, talking to Hawking was a bit like talking to the Oracle of Delphi. And And moreover, in the later years, it became very, very slow. So we developed all sorts of tricks to communicate, just like you do with your kids or with your husband or wife. So it was very interesting. In a way, our collaboration became in some way intimate because we had to develop a sort of a common language. The reason this quote is interesting is twofold. First, sociologically, here Stephen, far away from the cameras, of course, is stating that his bestseller is wrong. And the second thing which is interesting, of course, is that he identifies an age-old perspective rooted in all of physics, which turned out to be the key to the solution. And so let's take a step back. We have this biophilic universe. For decades and even for centuries, we've tried to understand the universe and everything else in physics from a perspective as if we're outside the system we're studying, from some sort of Archimedean perspective. And in fact, that was the big discovery of the scientific revolution. The idea that we can look at the world in an objective manner. This started with Copernicus and Galileo. Newton encoded that Archimedean perspective in the way he formulated the laws of nature. And people who thought about the multiverse took this to the extreme and began to think about the multiverse, the universe, from the outside. But when it comes to this one question, how we relate to the laws, the biophilic nature of the laws, we have to change perspective. We have to realize that we are within the universe, looking up and looking out. So in some way, we have to try to turn cosmology inside out. We have to get us, we have to get our perspective as observers within the universe into our equations. And that had never been done. Kafka already realized this, right? So how do you turn cosmology inside out? In fact, the answer was waiting in a completely different corner of physics, in the realm of the microscopic description of the world, quantum theory. Here you see Niels Bohr, and again Albert Einstein, seems to be in a better mood. Two of the founding fathers of quantum theory. Quantum theory is very different from our intuition. It's a theory that predicts probabilities, it has uncertainty built in, it has all sorts of strange features, but the most fundamental shift in quantum theory is that the theory steps away from looking at the world from an Archimedean perspective. In fact, that's precisely the point, that subjective touch to quantum theory is precisely what Einstein didn't like about it. Einstein famously said that physics should be an attempt to grasp reality as it is, independently, however it is being observed. But Niels Bohr was more sympathetic to that move. No phenomenon is a real phenomenon, he said, until it's an observed phenomenon. So you could say that Niels Bohr is a little bit the Magritte of physics. Here you see Magritte painting himself, painting a bird while looking at an egg. That's how quantum theory works. You see, in quantum theory, a particle, an electron, doesn't quite have a position until you ask for its position, until you decide to measure it. Schrödinger's cat, here it is, a 2D version, isn't quite dead or alive until you look whether it's dead or alive. So quantum theory describes the world at some sort of pre-existence level, as an ocean of possibilities where a tangible reality is crystallized, is emerging through countless acts of observation. It is very much like how Charles Ives put it, the fabric of existence weaves itself whole. That's the deeper ontology behind quantum theory. And all I did with Hawking was to take that quantum way of thinking about the world and apply it to the early evolution of the universe. We tend to think of the evolution of the universe. Here we have a big U, there's the Big Bang, the universe expands. We tend to think of the universe as it has a history, it's out there, it's just what it is, and we come along. But quantum theory tells a different story. Quantum theory tells us that the history of the universe comes about through countless acts of interactions, quantum observations, through, the history of the universe weaves itself together. And so the bottom line is that if we think about the origin, the Big Bang up there, it's not just something which happened, a definite thing which set the universe in motion. No, we have to think about the origin almost in a retroactive manner. That's what the dotted line from the eye back to the past means. The question of the origin hides the origin of the question. And so Stephen and I look back to the earliest phase of the universe in that quantum way of thinking. So when Lemaître did that, as I explained you, when Lemaître did that, he bumped into the Big Bang, the singularity, he bumped in the frontiers of science, the origin remained outside. When you look back to the early stages in a quantum mechanical manner, you find something very different. You find a deeper level of evolution. You find that the laws of physics as we have them today, when you go back to the Big Bang, they unify, they simplify. Physics itself simplifies. The different laws we have today, the different particles, the different forces, they unify, they lose their specificity. And we've always thought that we would land on a unified, final, mathematical, truly foundational law of nature. That was Einstein's dream. But what Stephen and I discovered is that, in fact, this process of simplification, this process of disappearing structure, even at the level of the laws of nature, continues all the way till eventually even time and space lose their distinct meaning. Looking at the early universe, the evolution of the first instances of the universe this way, you see something very different. You see a tree of laws. You see a tree of physical laws emerging gradually through a process, through a fairly random process. You see something which reminds you of Darwin, which reminds you of biological evolution, which reminds you of Darwin's tree of life. And indeed, that is the bottom line of the hypothesis we eventually proposed. Here you have Darwin's first sketch of the tree of life when he was just back from the Galapagos Islands. And there you have again Lemaître's sketch of the cosmological evolution. For 90 years, we have tried to understand these two very different levels of evolution on epistemologically distinct footings. Darwin biology is all about emergent regularities, emergent laws. Physics, cosmology, was always about immutable, fixed, transcendent laws. The deeper crux of our hypothesis is that this distinction was a mistake. That these are two levels, two vastly different levels of a unified evolution, which if you trace it back to the earliest stages of the universe, implies that also includes also the genesis of the physical laws themselves. So the answer we came up with 20 years, I'm sorry it took 20 years, the answer we came up with to his question that he posed in '98 was, in fact, deep into the Big Bang is hidden a deeper layer of evolution. And hence the title of my book, of course, On the Origin of Time, is nothing but a wink to Darwin's On the Origin of Species. That's in a nutshell, our, here we are in the Morse bit. In a nutshell, my journey with Hawking and what we figured out, or what we think we figured out. As many of you will know, he died in March 2018, and his ashes today are buried in Westminster Abbey. And in fact, his ashes are nicely in between the graves of Newton and Darwin. I'm not sure whether the priest in Westminster knew what he was doing, but I think that's a very appropriate place for what remains of Hawking to rest. Perhaps in the last 5 minutes, I'm now going to look ahead, look towards the future. Because, of course, this entire story of my work with Hawking is just one little facet in a much bigger story, which, of course, is not finished. And so I want to highlight 2 directions in which I think this is going to further develop in very, very exciting ways in the coming years. The first is more conceptual, theoretical, and it has to do with what I already told you. What I told you, for the philosophers among you, is an attempt to crack open physics. You know, since Newton, since Galileo, physics is all about laws of evolution, laws of motion. Physics is not about initial conditions, boundary conditions, the specificity of your system when you start it out, when you launch a rocket or whatever. That's not part of the laws. These are the laws. And physics is also not about measuring, the process of measuring. That's typically kept outside the laws as well. But the story that I've told you is that this is fine, except when you push these laws of dynamics to their limits, back to the Big Bang. So it seems there is ultimately a more general notion of a physical law or of laws of nature, which in most circumstances we can reduce the laws of dynamics, but which is at its heart more general. And that general notion is what we had been trying to conceive of, to develop. Technically, it's really a research domain which, as you can imagine, tries to marry quantum theory and gravity, tries to bring together the macroscopic and the microscopic descriptions of the world, the 2 pillars of 20th century physics. And why do you want to bring this together? Because the big universe was small at the Big Bang. The 2 have to work together. It's one coherent reality. And the surprise of the story is that if you want to marry the large and the small, you're also bringing in us into the equations. The perspective as observers within the universe, that is a truly unified theory. And so what is emerging from that marriage of quantum theory is the idea that time, the dimension of time, is a truly emergent quality of the world. Going back in time means losing more and more information. It's sort of quantum information picture that emerges, and going all the way back to the Big Bang is pretty much like how Lemaître imagined it. It's almost like you run out of bits. The laws of physics run out of bits and don't reach further back. The Big Bang becomes an epistemic horizon once you weave in the picture or observational perspective from within the universe. So there's a certain finitude to this story, a finitude, a finiteness, a limitation, a fundamental epistemic limitation, which strikingly, at least to me, was anticipated by no one else than Hannah Arendt. So you know that Hannah Arendt wrote a book, The Human Condition. She was concerned with all sorts of forms of alienation. And she was concerned with science and technology, the notion that we view science and technology as objective truths. She thought this was a self-defeating paradigm. And so late in this book, which, I didn't find easy to read, but in the second part, she looks for the deeper roots of that, what she called world alienation. And she traces the roots of that disconnect all the way to the scientific revolution, to the idea that we can look at the world in a purely objective manner. And she argues, towards the end of that book, if science is going to be truly flourish, to provide a truly new worldview, this cannot be correct. Somehow, even deep into the fundamentals of science, there must be a trace of our, what she calls then, our human condition, the fact that we are not disconnected like God looking upon the world. And of course, she looks into the science of her day, the 60s, the 50s, the 60s, and she doesn't find it. Everyone in the scientific world was happily practicing science from an Archimedean perspective. So the hypothesis that I developed with Hawking, I dare say, is a response to Arendt's concern. It's a call from the depths of physics that we should conceive of the laws of nature in a relational way, that we should conceive fundamentally of the universe as our home and of the laws that we discover to describe it in relation to us. Stephen and I wrote down an equation. The equation includes us, and it allows you to go back to the Big Bang, but at the Big Bang, the equation closes itself off. The second thing I want to say is the obvious thing. How do you test this hypothesis? Right? How do you gain access to this early phase of the universe where even the laws of physics exhibit an evolutionary character? The first fractions of its existence. You can't look back, you can look far back in time using light rays that originated billions of years ago, but you cannot look back all the way to the Big Bang. The early phase, the first 300,000-400,000 years of the history of the universe was not transparent. Light couldn't travel. It was a big fireball. It would be like trying to look inside the sun. You can't do that. So are we never going to find fossils of this early phase of evolution, this deeper layer of evolution which we think exists? Well, there is a way. And I've mentioned it already. There is a way. These are these gravitational waves. These gravitational waves, not light waves, these ripples of space that travel at the speed of light, they go through everything. They don't care about the universe being a hot fireball. And so there are two experiments underway. €2 billion experiments, one led by ESA, the European Space Agency, to launch 3 satellites 2 million miles away from one another, orbiting with us around the sun, listening to gravitational waves that are generated in these earliest stages when the tree of laws originated. And there's a sister experiment to this one called Einstein telescope, which is a similar construction but under the ground here on Earth. Again, lasers connecting a triangle, measuring the distances to an exquisite precision in order to listen to these gravitational waves. This is a true Galileo moment. We're beginning to listen to the universe in a completely new way, and what you're gonna see in the next 20, 30 years is that we're gonna rewrite the history of the universe using observations of gravitational waves, and ultimately peek through to all the way to the beginning. So that gravity arc, which I told you about, which started with Einstein, pure mathematics, no observations, no guidance, pure theory, which led to Lemaître's discovery of the Big Bang, which was then observed with the afterglow of the Big Bang. And then we realized that there might be hiding a deeper level of evolution, will in the future lead to huge experiments, big science, it's like building a new CERN. So in a sense, this gravity arc, which has been going on for more than a century, is now coming to fruition and may ultimately lead to new worldviews. There are very few arcs in science that go so deep and that span so many generations. That's really the beauty of this story. Thanks.